Hi, this is Alex Cosmander from the University of Arizona Cooperative Extension's WaterWise program in Cochise County, Arizona. In this video, the University of Arizona climatologist Mike Crimmins dives deep into the climatic context of the state of Arizona, including topoclimate, which is the study of how landforms and elevations affect climate areas, the seasonal distribution of precipitation in this area, how evaporation and plant transpiration make our area arid, plus what we know well and not as well about our climate as the planet continues to warm. We hope you enjoy this video, and please let us know in the comments what you think. My name is Alex Cosmander. I am the WaterWise Youth Coordinator, and joining me are Trevor Lauber, who is our Community Outreach Coordinator, and Mike Crimmins, a U of A climatologist. We respectfully acknowledge that Cochise County Cooperative Extension operates in the ancestral homelands of the Chiricahua Apache, the Tohono O'odham, the O'odham Druid, the Sobai Puri, and the Ho'opono. Committed to diversity and inclusion, the university strives to build sustainable relationships with sovereign Native nations and Indigenous communities through education offerings, partnerships, and community service. If you are not sure which native land you live on, I definitely encourage you to go to native-land.ca. It's a very helpful interactive tool to show which land you live on. Trevor, you want to take that away?
Absolutely. So I have had the pleasure to hear Mike give talks on climate in the past before, and if you haven't heard him, you're in for a treat. So Mike Crimmins is on the faculty of the Department of Environmental Science at the University of Arizona and is an extension specialist in climate science for Arizona Cooperative Extension. He has been in this role for 18 years, working with ranchers, farmers, and natural resource managers across Arizona to integrate climate information in their planning and decision-making and assisting them in developing strategies to adapt to a changing climate. If you have not heard it, Mike also hosts the Southwest Climate podcast, which I highly recommend. It's wonderful. A lot of good information.
Thanks, Alex and Trevor, for inviting me to talk with you all tonight. And good evening from this beautiful winter evening. Boy, we had quite a winter here in Arizona. We haven't seen a real one like this in quite a while. So I'm going to talk a little bit about everything from Arizona climate. I always give a disclaimer. I'm not a native Arizonan. I am from Michigan. I grew up in Michigan, went to school at University of Michigan, studied meteorology, and moved out here when I was in my 20s, and ended up going to school at U of A and studying climatology. So I've been here in Arizona for over 20 years now. So almost half my life here in Arizona. So Midwesterner by birth and training in weather and climate. And so really have spent the last 20 years trying to wrap my head around how things work down here. And they're so much different than back east, if you're from back east. Very interesting climate. And I honestly think that having a little bit of the mechanics down and a little bit of the physical geography of Arizona climate helps us understand how the climate is changing and how it will change into the future. Because the way that climate change imprints on a location really does have a lot to do with how things work in those locations. So how the climate changes in the Northeast, the Midwest, and the African continent are all going to be a little bit different based on the background climatology. So we're going to talk a little bit about that. So when I move through this presentation, it's going to start off with this climatic context. We'll look at some maps, we'll look at some time series data, and then we'll look at historical changes. We're going to look at the last basically 120 years of measured climate here in Arizona. And then we will shift into thinking about some of the basics of climate change science, and then looking at some of the projections here. So hopefully it'll be kind of a seamless sweep from past to present to future. Okay, so I jump right here. And if you've seen any of my talks before, I love this map. So I always start off with this map because I'm a kind of a map person to think about climate. And we can do really amazing things with mapping out climate right now. We have remote sensing satellites. We have long-term networks all over the globe that have given us over 150 years in some locations of actual measured temperature and precipitation. And we've come up with really clever ways of actually looking even deeper into the past with something called paleoclimatology, where we can core trees, we can drill into ice, we can drill into corals, and actually look at how the environment has captured measurements of climate into the past. And especially in the paleoclimate, if you haven't had a chance get to Tucson and tour the laboratory of tree ring research, which is really the home of dendrochronology and some elements of paleoclimatology. It's really pretty impressive, and there's some really nice tours that can come through there. Okay, so jumping back to this map, this is a map of station data. So we have measurements at stations, weather stations all over the world. And what we can do is we can take those stations, and they're not going to be at every location across Arizona, but what we can do is we can actually put them on an elevation map. And what we know through these measurements is that upper elevation locations are going to be cooler on average over time. Lower elevations are going to be warmer on average over time. So those differences between elevations, we can come up with statistical relationships and do something called interpolation, where we actually estimate what the climate might be between stations. So if you notice on this map, there's little pixels or little squares all over the map. And that's the resolution of the elevation model that we use here. So we take those stations, drape it against the elevation map, and then estimate climate. And so here we have long-term annual average climate across to Arizona. And some things that I think are fairly obvious, but nice to see on a map, is that Yuma is much warmer than Flagstaff because they're at very different elevations. And we can see the subtle gradients that emerge from elevation. And so elevation is a important organizer of climate. And we actually call it topoclimate. So it's topography-driven climate. And so these long-term features organize along elevation gradients. So when you live in a place with mountain ranges and real sharp gradients from valleys to mountaintops, you have dramatic climate diversity over short distances. And what we can see here too is that diversity then, well, we know this by observing it, is that the plants often tell the story of the long-term climate because they've organized around these climatic features. But kind of in your mind's eye, think about what this map would look like back east, for Iowa, or from where I'm from Michigan, right? What if we kept the same color ramp? It would be almost one color, right? So as you move into the Western US, we have this added dynamic of having topoclimate that we actually have to think about and deal with and measure, and then contemplate how that'll change into the future. So this map, clearly just a nice elevation map showing us long-term average temperature. So if we flip forward, and I'm really going to dance back and forth between precipitation and temperature this whole talk. I'm going to talk about historically how those changes. I'm going to talk about how they've interacted with each other into the future, and then we're going to look at some climate projections of both temperature and precipitation. So this map, same way, precipitation measurement interpolated over distances. But you may notice that it certainly does look like an elevation map. We do see the features where lower elevations tend to be drier than higher elevations, which are wetter, but not every place organizes is cleanly and evenly over space like temperature. Some places that might jump out to you are the northeast part of the state, which is actually about 5,000 feet. So it's similar elevations to parts of southeast Arizona, but it's much drier. So that is the high cool desert of the Colorado Plateau. And that's actually a desert because of the effect of the Mogollon Rim, where, can you see my cursor? Do I need to turn on okay, good. Use my cursor here. This is the Mogollon Rim right here, this topographic feature. So as weather systems during the wintertime come from west to east and move across the state, the low-level moisture is pushed up by this topographic feature, condenses, rains or snows out, and then descends the other side, drops in elevation, dried, the air is dried out, it's compressed now as it's experiencing higher pressures as it goes down in the atmosphere, and it dries out. So it's called a rain shadow. You may have heard of that before. Big rain shadows in the continental US are like Death Valley on the east side or the lee side of the Sierra. And there's in the Cascades up in the Pacific Northwest also have much drier land on the lee side or the east side of the prevailing winds from the west across the Cascade Mountains. So we see these little subtle features in areas that have prevailing winds, large topographic features. You can get dry areas on the lee side. So we see that organizing out in the northeast part of the state. Some other areas, the very, very low elevation parts of the Grand Canyon, you can see here kind of barely show up on the pixels, but so much more atmosphere. As storms move out over the Grand Canyon, they may put down a lot of snow at the top on the rim, but as that snow falls through the deeper depths of the Grand Canyon, it can get warmer, it can get drier, it can evaporate that precipitation, so it's not quite as wet, the lower elevations. And we see that, that's, if anybody's familiar with virga, we'll see virga often in the springtime as things start to warm up and dry out. That's those rain clouds with the shaggy shaft of snow basically come out of it, and then it disappears about midway in the atmosphere, and all that's falling from the remainder of that is cool, dry air spreading out. And so in semi-arid, arid regions, you see quite a bit of those features. So we see topography here with the Mogollon Rim. The southeast part of the state, where most of us are right now, have the monsoon during the summertime, which favors the southeast part of the state, can fill in those valley locations much more effectively than valley locations in the northern parts of the state. So really interesting dynamics at play all across the state, just on the background climatology with topoclimate. Maps like this just bring it all together. And so it's very similar data. The upper left is the elevation map, much finer scale, so even finer than we were looking at right there. So you'd know by just looking at a map like this, higher elevations are cooler, lower elevations are warmer. Higher elevations in many locations are wetter. Lower elevation locations are often drier, but depending on the state, parts of the state that we're operating in. And then this upper right map, I like to pull out, which I think is really interesting because it shows the topoclimate and topoclimatic diversity being reflected in the Arizona biome. So the ecology of the Southwest is organized around these precipitation gradients and also the timing of the precipitation, which I'm leaning into this next section I'm going to talk about here. And so if we look at this map, really interesting biomes emerge in our very southern latitude state at higher elevations. So these are some of these biomes you'd see up in Canada because it's so much higher latitude and at a lower elevation. But as you go up in the atmosphere, cooler, wetter conditions can support some of these biomes like conifer forests, even subalpine conifer forests. We can see woodlands and grasslands and desert scrub in kind of the mid-tier, and then the lower desert scrub regions of our major deserts across the Southwest. So the last point I'll make with this graph here, to draw your attention, and again, every time I see this graphic, I see Sonoran on here twice, and I'm not sure why it is, but this yellow and orange grouped together represents the Sonoran Desert region. But we have Chihuahuan, Mojave, and Sonoran Desert presented on this map. So in Arizona, the convergence of these three large desert ecosystems across the both continental US and into Mexico are coming together here. And the way I think about it is actually the seasonality of precipitation. So the Mojave Desert is leaning into clearly California and Nevada. And those regions have Mediterranean climates. So they get most of their winter precipitation during the winter and very little, if any, during the summer. So it's unimodal, meaning it peaks in that winter and you got these dry shoulders. So that's a really different way of getting precipitation than, say, the Sonoran Desert. The Sonoran Desert is in between. The Chihuahuan Desert is primarily summer, gets most of its precip in the summer and much less in the winter. So if you think about it, in between winter-dominated precip in California, summer-dominated in the Chihuahuan Desert to and southeast, Arizona is right in the middle, and that what we call a bimodal precipitation distribution. We have two potential wet seasons, so we can get winter precip like in this winter, but we can also have the summer precip like we saw the last couple of summers. And when those really sing together, you get pretty amazing things with soil moisture, water availability, and the ecosystems really sort of jiving on all of that additional precipitation. And when one precip season fails, we're not completely sunk because we can make up some soil moisture in another season. But when we have two seasons fail, not too long ago, not in our memories, we can think about when summer 2020 monsoon just really didn't show up, and then we were followed by a dry winter. So that's our worst case scenario. And that's again, the real challenge of thinking about future precipitation variability is models actually have to get both of those seasons right to converge on what those really deep droughts look like. Okay, so leaning into that seasonality, we can look at this a little bit closer across the state. So these little multi-county dashed lines here are something called climate divisions, long-term data going back to the late 1800s to present, where we can make these little things called climagraphs. And so these climagraphs are real simple, long-term average monthly precipitation starting in January, all 12 months through December. And the value doesn't really matter, it's the pattern. They're all scaled to be equivalent, but what we want to kind of look for is that thumbprint or that signature of the seasonality of precip across the state. So your eyes are probably drawn to some features already here. It's we look to the southeast part of the state, real tall bars in July and August, taller than anywhere else in the state. You know, the southeast part of the state is monsoon country. Other parts of the state can kind of claim they are, but really southeast Arizona is monsoon country. And that is because Mexico is the true monsoon country and we're on the far northern reaches of that. So as we look up into Arizona, that summer signal is still pretty high along the upper elevations because that helps enhance the monsoon activity. Further north, it starts to drop down a little bit. The low deserts don't have much of a signal because it's harder to generate that precipitation without topography, quite honestly. We can look in the winter. The winter, quite a bit lower in the southern parts of the state. Again, we're leaning a little more Chihuahuan desert. As you go north, higher latitude, a little bit closer to those storm tracks. Far northwest are leaning into that Mojave Desert kind of system. And then the very low deserts, really tricky to get precip in any seasons, which is, again, the ecosystems tell the story. It's very, very hardy creosote desert scrub, low biomass in our low desert areas. So again, just kind of keeping all this in the back of our mind about like, how does climate change affect these different systems? Okay, so this graph, again, is just, it's zooming out, and I know it's a lot on here, but I just want to articulate this idea of seasonality a little bit more. So what I've done with this is I've used an online tool. We've cookie cut out Arizona climate, those gridded pixels. We can basically average them all down to one number for each month. So it's the wettest and lowest locations. And so it gives us one number for all of Arizona. We can do it back 128 years, and then we can do statistics on it. So I take that monthly data, we just basically organize it from wettest to driest for each month for that 128 years. So the value for October precipitation, this black line, is called the median. It's the middle value. So this right in here in this blue region is the most frequent average Arizona precipitation we see in October. And then we can just plot it going forward. And it shows us the same thing we saw in those climagraphs previous slide, which is, here's our kind of, it's fall, lots of variability. We move into winter, it gets a little bit wetter because it kind of bumps up here in December. And again, look at that blue to light blue to very light blue range. That's the variability we've seen historically across Arizona in that 128 years for these individual months. So we have lots of variability in the fall, lots of variability in the winter. We see a lot of winter droughts, we see a lot of winter wet systems. Then we reliably move into the dry springtime here. You can see that those color bands, they shrink because there just is no such thing as very wet springs. We can't do it. We don't have the mechanisms to actually make it wet here in the spring. So pretty reliably that dries out for Arizona. So that's actually really useful background information to just look forward for expectations. And then look at that big jump up into monsoon precipitation, big jump up, and then much higher than the winter, a little bit less variability. Okay, so what have we done? We've done topoclimate, thinking about topography and climate across the state, the Southwest in general, how that organizes climate. We've talked about seasonality and how varying through seasons can give us wet seasons and very reliably dry spring, and then our monsoon. We're kind of coming and going as far as when we're putting down precipitation reliably. I now want to talk a little bit about the interaction between temperature and precipitation. And so this is where we get in conceptually thinking about, and I know everybody's kind of got this in their head already, but just again, a little bit of review. Very simple hydrologic cycle and thinking about concept of aridity. So hydrologic cycle, we've all kind of learned this I think it was in middle school, maybe I first started getting it, is precipitation rains out and there's movement and transport of water can go into the soil. It can go into deep soil and actually move into base flow, move into streams. It can go into deep groundwater. Largely, a lot of the movement of water in Arizona is at the top surfaces because we have high evapotranspiration. So precipitation moving into water bodies, groundwater and surface flow, evaporation, rinse and repeat. Okay, so the reason I start with there is because I want to talk about the concept of evapotranspiration, because this is really, really important for us to understand the climate change story in the Southwest, and actually across much of the world, but particularly in the Southwest. So evapotranspiration is simply a compound word of transpiration and evaporation. So evaporation, we all know, it's just water, free water, moving from liquid to vapor up into the atmosphere, right? Hand dryer at the rest stop, get them wet, put them under a hand dryer, evaporation. Transpiration is actually the use of water by plants. So when plants draw water out of the soil and use it for photosynthesis, they release water vapor into the atmosphere. So that's a really effective way of moving water back into the atmosphere. It's a huge flux when you have a lot of vegetation. You can move huge amounts of water much more efficiently and quickly than you can through just evaporating the water. So we have to look at those combined effects. So evapotranspiration. Okay, so in my world of climatology, I think of a conceptual term called potential evapotranspiration. So again, evapotranspiration is plant water use evaporate into the atmosphere, and then free water evaporation, just water evaporating from reservoirs, from puddles, from pools, from whatever open water bodies surfaces. So in the climatological world, potential evapotranspiration is exactly what it sounds like. It's the potential. And so think about, what are the days like when the potential evapotranspiration must be really high? It's days that are windy, very sunny, very low relative humidity, dry, cracking skin, and hot, right? So when all of those factors converge, the atmosphere wants water, and it's going to take water from any place that it can get. And so it will evapotranspire, be part of the evapotranspirative process by drying out the surface and carrying it into the atmosphere. It can turn into clouds. Sometimes it can just get carried off down wind and then rain out somewhere else. So it's part of the hydrologic cycle, is potential evapotranspiration. Potential evapotranspiration, though, it's limited by how much water is actually available. That's the potential part. So when you dry out the soil and there's no water left, there's no more actual evapotranspiration, but there can still be high potential evapotranspiration. So I'll make that distinction. So this particular plot right here is a climatological estimate. It ran for Tucson here. Daily, basically daily temperature drives this model. Long-term averages for January 1st, every day all the way through December 31st, and it's scaled in units of depth of water. So it basically says on January 1st, the long-term climatology suggests that the atmosphere would want about 0.07 inches of water depth. It could take that in the atmosphere. And that's very different than, if you notice on this plot, where it peaks right about January 21st, or I'm sorry, June 21st. What's special about June 21st? Longest day of the year, right? So that's where you get all of that evapotranspiration. You can see the differences in depth here. You can see how that trace increases as the days get longer. It gets hotter here, gets drier, and we peak. And then it starts to crash right after that, because typically monsoon moisture comes in, RH goes up, relative humidity, clouds come in, limit evapotranspiration. So we have a little bit of a kind of a dip there in the monsoon season where ET rates fall. And then as the days get shorter, that ET rate falls, and then we go right back into it in the wintertime season. So we're thinking about that in the background, follows temperature very closely. Okay, so the green lines are long-term average precipitation. So there's a lot of zeros in that, so they're quite low. But if you added them all up, it'd be about the average precipitation for Tucson. You can see there that wet signal kind of in the winter, very dry in the spring, big jump up in the monsoon, and then kind of the noisy fall season. Okay, so that's our background climate. But what I want to do is go down to this next plot here in the bottom. And this is cumulative daily precipitation and potential evapotranspiration. So it's adding one day to the next and running that total forward. So as we look at, by the end of the year, the annual potential evapotranspiration is about 65 inches of depth of water. So that's how hungry the atmosphere here in Tucson is for water. It wants 65 inches on average of water. How much is it actually given by precipitation? About 11, right? So I think of that as a checking account, right? You got an $11 paycheck, but you had a $65 bill. You can't cover it, right? So you're in deficit. You actually have a deficit there, and that's what an arid climate is, right? So that's just our background climatology. We'd never ever get enough water to meet this potential evapotranspiration. Even in wet years, we can come close, but we're always sort of falling behind. And again, the plants tell the story. What the plants' long-term water deficit that they're dealing with is they have adaptations. And so if we want to overcome that, we have to irrigate, we plant different kinds of plants. Okay, just to kind of put a little further point, I'm going to skip that one. Look at a couple of different cities, same stats, same idea. Phoenix, a little bit lower, a little bit warmer than Tucson. Look at the stats here. So a little bit more PET, 67 inches, and annual precip coming in is 7. So it's even a little bit more, right? So if you go down to Yuma, a little bit lower, a little bit hotter, less precip, it grows even more. And the plants tell the story because we have that aridity. We can jump up to some of our wettest places in the state. This is Flagstaff in particular. You can see here that on average, there's some times of the year where PET is so low, we actually do get enough precip to overcome that. We still have the spring dry signal here, still high levels of PET with low levels of precip. The monsoon comes in and tries to do its work, but it's also a very warm season. And then we finish out the rest of the year. So the total here is 47 inches for PET and the annual precip. So much closer, but still a deficit. But again, the plants tell a story. There's actually soil water that accumulates and turns into base flow of streams, and water actually runs for part of the year in those locations because of this little bit of surplus, right? So again, that's actually topoclimate interacting with seasonality and interacting with aridity, thinking about these different levels across Arizona. Again, okay, just kind of building your basic knowledge of Arizona climate. Okay, so let's look backwards. Let's look at actually some of the time series over the last 128 years here. And I'm pulling data, same kind of data I was showing you before, and you can go on the site and check it out too. It's a really nice feature, West-wide drought tracker. And you can make maps and pull long-term time series. And I'm going to show you some of these time series here. Okay, so the first map I'm going to show you is updated right through last calendar year. So it's only a month, 2 months behind, month and a half behind. So it finishes up with calendar year of 2022, which is this last bar right here. And again, think about it again, it's Arizona as a whole, the average precipitation over the whole state for the whole year. So there are going to be some locations much, much wetter and much, much drier. We're averaging them all out into one number, which is each of these bars. Okay, so we can go back all the way to 1895, and I plotted in 1900 here. No, actually, I did 1895. This one, sorry, the label is wrong in the bottom. 1895 to present, we have this data. The black line here is the long-term average, and this orange line is the 10-year moving average. So it just kind of smooths out some of this variability, so we don't get lost in all the year to year. So you may know this is the long-term average. We have lots of variability from year to year. We have very few years that are like hugging the average line, you know, like once in the teens, once in the 30s, once in the 50s. We do a lot of above and below. We have a highly variable climate just normally. And we can also see here too, if you notice this orange line smoothing out some of this we have decades where it's kind of hangs above average on average over time. Dry decades here in the 50s, this is 50s drought era. Very wet, we call it pluvial is the fancy word for a wet period in the climate record here in the 80s. And then this is our most recent drought, which you can kind of link back to the late 90s. And we've been bumping along since. It's flipped up a little bit in the last couple of years, gives me maybe a little bit of hope. Could be a fake out too. That's the problem with this climatology, that looks a lot better looking backwards than it does forward, because forward we have to predict the future. But we've had a couple of pretty bad years in here. This was 2018, if everybody remembers it. That was one of the bad drought years since 2002 across the state. Very, very dry fall and winter season, quite a bit of fire activity following that as well. But this is what it looks like in the long-term precip variability. Okay, so what we can do is I'm going to flip this around and turn this into a drought index to really make it pop. So we can see these wet periods and dry periods. So blue bars are wet years, and these are in standard deviation units. So the wettest year in record will have the highest standard deviation value, and the driest will have the lowest. And so blue bars are wet years, red bars are dry years. Again, kind of draw your attention to early last century drought, 50s drought, bumped along for quite a while, wet period in the 80s. This is our most recent drought. A couple of wet years on average have popped up here, which have been a little bit encouraging. Okay, so now we can weave in the climate change story on top of this, is that we have a temperature trend, all scales across the planet, globally, and we can go all the way right down to locally and regionally here. And so this is again, Arizona statewide using this data set. So it's not driven by urban heat islands or any other kind of variability. It's got all of that variability sort of baked into and smoothed out by this large regional picture. And we're not talking about decadal variability anymore. There's a little bit of wiggles here, but there's a trend. There's a pretty strong trend. And this is consistent we've seen globally. So in the last several decades, especially since the 90s, we've had runs of above average years, a cool year here and there. In 2018, I remember that very dry year was also one of the hottest years on record, and we continue to keep above average because it's consistent with the global trend. Okay, so bringing them together, thinking about this concept of aridity, higher levels of evapotranspiration occur with higher temperatures. So if we have a temperature trend occurring across the state, that means on average over time that evapotranspiration is also going up. And on average, things dry out. And so even during I'm going to show you a couple of plots here, is even during really wet winters, they aren't quite as wet as they used to be when the temperatures were lower, because again, all that extra energy with increasing temperatures liberates more of that water vapor out of the region. So it makes a dry region drier because of increasing temperatures. This drought index is cramming those two things together. So it's both precip and temperature trend on top of each other. So you can see here the 50s drought looks like the 50s drought here, not that different because the temperatures weren't quite that different. But the more recent drought is much deeper, more extended because of the on year after year above average temperatures increase that drought intensity. So again, that to me is the long-term challenge for the Southwest, increasing temperatures, wild precipitation variability from season to season and within the season, but if it's getting warmer over time, the effective precipitation goes down and we're dealing with increasing aridity. Okay, so this map, there's some really great maps on here. This map on the left is, it's a drought index, and this happened to be last spring, I think I pulled this map. And so it was coming out of really wet monsoon in 2021, mediocre winter. And so this drought map was painting white conditions here on the map are near average precipitation. Green is above average, so lack of drought. The oranges are drought, but it was also really, really warm because of long-term trend. And so this drought index, which makes it look pretty good, when you add temperature to it, you get this drought map, which is probably more realistic. See how the increasing temperatures have eaten away at the gains of having that benefit of precipitation. The increasing temperatures pull that extra moisture out. These indices are not perfect, but they're pointing towards the challenge rather than being the absolute kind of quantification of it. Just to show you too, more recently, this is the map from last May through the monsoon into the fall and ending last month. So starting last May, we had a great monsoon across much of the Southwest. The fall was really wet. The last couple of months have been really wet. So this is the precip drought index situation across the West. It looks really pretty good. These are rare wet values up here. This is the temperature. So even though it's been wet, we've actually had above average temperatures for much of this region. So that again is a little bit of the buzzkill where these wet conditions, when we add them together, you can see how the gains made by the precip are being challenged by this increasing temperatures here. And you can see across the Southwest where those really deep blues turn to greens and whites because of increasing temperatures. Okay, cool. So that's it. So like that, and that's not it, but it's like, this is the background to move into the climate change discussion. Okay, so excuse me, this little bit of background, just a little primer again on the greenhouse effect, what the concern is, what the physical mechanism is here, is that it starts with the sun. Sun's really important, warms the planet, creates all the energy, makes the photosynthesis for all the food that we eat, really critical. The sun's energy comes in as shortwave solar radiation because it's really high energy, hot temperatures. That shortwave radiation moves through our Earth's atmosphere unimpeded. It's just the constituent gases we have. Once the sun's energy strikes the surface, a couple of things can happen to it. If it strikes a highly reflective surface like a white roof or snow, it can actually be reflected back out to space and no harm, no foul. The energy is basically lost. If it's absorbed by anything dark, like a dark blacktop parking lot, that energy is slowed way, way down, turns into thermal energy, and then is re-radiated as long-wave radiation. And so when long-wave radiation tries to go back out into space, we have all these gases in the atmosphere, like this cute little carbon dioxide molecule in the lower right, that are very excited by long-wave radiation. And so what they do is that there just happen to be the right molecule to interact with long-wave radiation. And when they do interact with it, they start to wiggle. And when they wiggle, they give off long-wave radiation up and down. And so when they do it down, it's extra energy coming back into the planet. So it slows up the whole system. Long-wave radiation is sensible temperature change. So we actually have heating. So the more CO2 or greenhouse gases we have, nitrous oxide is one of them, methane, also water vapor, more of those mean less of that energy at the surface can go back out to space. So it's held here longer, and then it creates warming at the surface. So that's the whole thing, the greenhouse effect. So when we want to try to, we know that physically, we've actually known that physically through physicists experimenting with greenhouse gases in the 1700s and 1800s. So this is not new, been in the physical science literature for several hundred years. We've known this is going to potentially be a problem since the 40s and 50s, and then it hasn't been until we've gotten into climate modeling in the 70s and then the 80s and up to present, where we've really been able to bring a lot of those moving parts together to do something called attribution. So in science, we develop hypotheses through the scientific method. And so to be able to prove something scientifically, we need to do an experiment. And so climate science has to build models to be able to do experiments. We don't have control planets. We don't have an identical Earth in the same spot that has no change in greenhouse gases that we could compare it to say, that's not changing, this is changing, that's why temperature is not changing here, temperature is changing here, right? So that's how we would normally do it, benchtop experiment. Can't do that, we build models. So here's a figure that came from an IPCC report about 30 years ago, and it's been updated since, but it has the same gist of the idea. It's, okay, so if we build a model, we put in things that we know influence the climate, like volcanic eruptions cool the planet temporarily, but then warms up again. We also know that solar variability on the solar cycle, 11-year cycle, varies the sun's output slightly, and we have little variations in climate. So we could build a model using that and then run it forward. And that's what this blue line is. And the envelope around this is the variability. We can also build a model. We'd have that would be the control. The manipulation would be to have all that same stuff in there, but let's change the levels of greenhouse gases in the atmosphere and see if we actually have an effect that matches this black line, which is actual observed temperature. So this simple experiment gives you an output where over the last 50 years, the experiment that has greenhouse gases in it is the only one that really matches the observed temperature change. So that's how we can attribute changes in CO2 to anthropogenic climate change and not just natural variability. Natural variability would be this blue line without having that enhanced additional energy in the atmosphere from increased greenhouse gases. Okay, all right, so getting into climate modeling, this is where it gets to be a deeper and deeper rabbit hole of information, because there's so many moving parts and so much going on. To do climate modeling, climate models are sophisticated mathematical models that are run on supercomputers because they have very, very fine scale moving parts. small geographic areas up through the atmosphere, and then are trying to do it at 30 minutes over the entire globe and then over 100 years. So all that mathematical equations have got to get solved at every little step going forward. So that's just the climate model. But when we want to actually do something called a projection, we want to figure out what it's going to be like at end of century. We have to guess on an educated guess on what might be the levels of greenhouse gases in the atmosphere. So that's not a physical science, pure physical science question anymore. It's actually a policy question. So there are teams of political scientists, technologists, economists, physical scientists who do all sorts of different things, social scientists, all then trying to get together and think about, okay, if policies change in this way, greenhouse gases might go way up. If we have this change in 20 years, we guess that some new technology comes online and we go up for a little while and then drop down. These are called scenarios. Okay, so we've been using scenarios again for a couple of decades, and we've had some we call them storylines now, some storylines that have been very, very optimistic and very, very bad. And they're kind of the guardrails on the way we think the system works. Okay, so the worst case no policy outcome is about a 5 degrees Celsius change across the planet by end of century. Okay, so this is often called 8.5 if you see it on any climate projections. That's the high end one. Okay, and then you'll often see a couple of other ones. You'll see 8.5, 7, 6, 4.5, and 1.9. These are actually all numbers in units of watts per meter squared. And so it's the extra energy in a square meter that's being re-radiated down from greenhouse gases. And so if you remember what remember old Christmas lights that were incandescent, that weren't LEDs, they gave off a little bit of warmth. So one of those was 1 watt. So if you had 8.5 extra Christmas lights for every square meter across the planet, that's a lot of extra energy going down. And it goes all the way down to trying to keep it at an extra 2 Christmas lights per watt per meter squared across the planet. Okay, so the reason this is important is that when we present projections, we need to then think about, well, what is the future storyline it's using? Because the model is going to then take greenhouse gases in the future and one of these traces. All right, so this is a story from Zeke Hassfather, who's one of the IPCC reports. He's one of the scenario scientists on IPCC. And what's been interesting is that things are getting better. And this is why I find this is part of a kind of a hopeful part of it is that he published this paper in Nature, and really the operating space is not this whole range of outcomes anymore, largely because we've had changes in technology, shifts in energy policy, and pledges that are narrowing the range of outcomes. So what he has noted through his work, and he wrote a paper on it by doing some analyses, have found that you can actually ascribe probabilities to these outcomes. So this is highly unlikely. It'd be really hard to get to 8.5. We'd actually have to reverse policy and work really hard to get every bit of fossil fuel out of the ground. That seems really unlikely at this point. And even some slippage would be unlikely to get us to 4. So we're kind of working down here in this likely range, which is what we're calling weak mitigation, modest mitigation, a little bit more enhanced, and then the Paris Accord. So the Paris goals are down here, and you can see that they're really the most aggressive. They're also the policies that we should be pushing towards, because it has the most climate safety across the planet. This is much better than 5. It's not as good as 1.5. So like if we get to 2, that could be really good. We should continue to push for 1.5, but this gives you the range here anyways. The reason I say this, I'm going to show you some projections here that are 8.5, so don't freak out because they're highly unlikely, and then a 4.5, which is down here in modest mitigation. Okay, and the reason is because the tools out there right now of the old generation, before we really kind of understood these scenarios, used 8.5 and 4.5 to put the data out. They're getting a little bit better, and hopefully we'll see the next generation of tools with more scenarios. So you can go to the site and play around with it. It's a future climate dashboard on the climatemapper.org. Drop the pin in Sierra Vista. Again, this is a higher emission scenario for summer temperatures. It runs through the different decades here. And you can see here that By end of century, it's about 10 degrees warmer than it was in the 90s. That's a huge, huge shift, right? That's like Sierra Vista becoming Casa Grande over the next century. We don't want that. That's not a great outcome. But I want to show you here too, the temperature traces are all pretty consistent. The changes in precip here, and boy, we see this with just about all the models. We've seen it for generations. We see it with the new models, is that they just don't latch on to any big changes in precipitation down here. You can see over time, the average precip doesn't really change much, but the PET does. So you can see here it was 77 inches in the 90s, and it's now 90 by end of century. Again, higher emission scenario. Okay, so let's break these apart. We can actually look at the two different emission scenarios to get a sense of sensitivity. Okay, so red line is high emission scenario, highly unlikely at this point. The lower emissions range is more likely, we should do better, is also the outcome with this. So you can see here by end of century, quite a bit warmer with higher emissions, still quite a bit of warming, consistent with what we saw with those other figures of a couple of degrees warmer on average in the winter. And in the summer, you can see here that they climb up even a little bit higher and faster with the higher emission scenario. And they level out here with the 4.5. Granted, warming is basically in the pipeline. How much warming we can claw back is dependent on the emission scenarios that we get at. Okay, precip for Sierra Vista. This gray area around the black, this is that crazy, that's our variability, right? We have wide guardrails. We swing wildly around the median. And in the future, kind of the same, right? A little bit of a lean of drying out, but it's not consistent. You see very little of this in the climate models, even the next generation. It's kind of a shrug. We don't expect any major changes in the climate system. Precip-wise, we think the monsoon's going to continue to do its monsoon thing. We think El Nino, La Nina are going to continue to do their thing. There's probably some things we don't understand yet that could make ENSO more extreme, maybe fewer events or more events, but they would add up over time, probably did not huge shifts, but maybe extremes emerge in this time series. And it's same here with the monsoon season projection down here. Okay, but last couple of slides, I want to lean into, those are, okay, so let me step back here for a second. Modeling, there are modeling groups, about 30 of them all across the world that run their own climate models, all different countries, different meteorological agencies, and they all participate in something called the Coupled Model Intercomparison Project, where all of those teams are given the same scenarios to run. So we all have comparable answers. So we're at CMIP 6 right now. That's the most recent results that have come out last year. So they're real fresh. I was showing you CMIP 5 results, so it was the previous generation. It's about every 5 years and it moves forward. So this is now the hot off the press projections for the Southwest. It was a really interesting paper written last fall that focused on the Southwest, our neck of the woods. So what they found here was, this is a quote right out of the paper. It says, robust declines in precipitation over Southwest North America occurred during the spring and are centered mostly over Arizona and New Mexico and only emerge in the moderate 4.5 we talked about and the high warming scenarios. So this is telling to me that if we continue to let emissions drift, we drift into more spring drying. And that's what we've kind of known that for about 20 years. And springtime drying means that we dry out quicker in March and April than we used to in the past. May and June will always be dry. They've never really been wet, but we eat away at winter. We make winter shorter and we have a longer dry spring. And so that's coming up. But it also says that in the lower emission scenarios, we don't see much change. That's good. So that means that mitigation can actually affect change in Arizona's climate. So just looking across all these panels here too, I don't want you to stare at all of them. There's too many maps here. I'm going to zoom in here and look at a couple maps. So the top row here is winter time, and the left column is strong mitigations. That's 2.6. That's better than we're doing right now. Not a lot better. I mean, we could get there pretty easily. We should even get more down to like 1.8, 1.9. 2.6 would be good. And then 4.5 is us drifting and dawdling more. What's interesting about this is in the wintertime, these crosshatch patterns mean that the models aren't agreeing. Some are going wet, some are going drier. So that gives us low confidence. And we've known that too, is that precip projections aren't super confident. So in these situations, there may not be much change in the winter, but in the springtime, you can see there's lack of model agreement under strong mitigation, meaning that maybe we could keep the change low, but if we let it drift, this is that, see where the crosshatching goes away from over southern Arizona? That means, oh no, the models agree then if we let greenhouse gases go that high, it will get drier in the spring. And that would be a continued trend of current conditions. Okay. The challenge on top of this is going all the way back to we talked about aridity, is that temperatures keep moving up. It kind of doesn't matter if precip changes or not. The effective precipitation will continue to change as the temperatures warm. So, you know, if we're getting good monsoons and good winters, as it gets warmer, they're not quite as good as they used to be in the past. And this is a concept called vapor pressure deficit. It's just another fancy term for evapotranspiration or drying effect in the atmosphere. And so you could see across here, the degree of that drying is commensurate with how high the scenarios get. So less mitigation, more greenhouse gases, and higher levels of drying that we've got to deal with. And you can see here in the springtime and the summer, it gets really pretty gnarly in the summertime. And there's still work for us to be done to understand the interplay between monsoon precip and this drying, and if they can cancel each other out and how much they can. We don't really know right now at this point. Okay, so that's my final slide. So I'm going to wrap up here, try to bring it all home. So higher temperatures, higher evaporation and transpiration rates. We're really confident in that. Increased water loss in reservoirs, faster drying of soils, falling precip events, more stress on veg. There's shifts in the hydroclimate that can mean less snow, more rain in winter. We're seeing this in research over and over again. Gets a little bit warmer, snow levels go up a little bit higher. We have less snowpack in the spring to actually generate stream flow. We're already seeing longer growing seasons across the state. If you're a master gardener or just a backyard gardener, you know we've had some winters where tomato plants have stayed alive all year round. This winter is a little weird. I've had a couple of hard frosts. This is actually the way it used to be in Arizona. This is quite normal, but it's just a taste, and we can't hang on to this with trends. So it's enjoy it while it lasts. And then the precip projections are lower confidence. We talked about that all the way through. Higher temperatures, though, give us confidence that we will have shifts in effective precipitation, regardless of us understanding how precip might change in the future. And we got to watch out for increasing variability, extremes from wet to dry and droughts to floods. Okay, talked at you a lot for 55 minutes, so I'm happy to field any questions. Hang around as long as you want, and you can always reach out to me later as well. And I can send this presentation to anybody. I can email a PDF to you if you're interested in checking it out a little bit more.
Mike, this is Judy from Sierra Vista.
Hey, Judy.
I think I blinked, and so I missed the meaning of SPEI.
Good call. I probably didn't explain it. It is.
Oh, there it is.
Yeah, so it's a drought index called the standardized precipitation minus evapotranspiration index. So
yeah,
most of our drought indices are only precipitation based. This one is the additive effect of temperature and precipitation.
Okay, and that one I get now. I just couldn't figure out what SPEI was. There we go.
Yes, a lot of acronyms.
I was a little curious about, because I've heard about there being the difference between drought and aridification, and I'm curious how much drought constitutes aridification.
Yes, it's a really good point. So the climate community has had trouble untangling them. So in the Southwest, we're already a water limited system. So we have lots of variability. Like we have seasons where it doesn't rain at all, and that's quite normal. We have winters that fall down and lead to drought conditions. So that's most of the signal. When you look at a climate trace, the wide swings are mostly natural variability and what we'd call drought. There's a little, it's the creeping crud. It's the little, the temperature trend makes those traces have a little extra on the highs and lows, or mostly on the lows and lows, eating into drought. And so they've enhanced it, you know, probably 10% on top of the additional, on top of the natural variability that we see within drought. So it's the temperature trend again it's consistent, it's persistent, it's always there now, and it's adding to the normal wide swings that we see going on.
Mike, for me working with water, I often wonder in the monsoon season, obviously we get a lot of our rain, but there's also a lot of clouds out there that are blocking the sun. How, can you kind of quantify through some of the stuff we talked about here? Does that have an impact on how much evaporation and transpiration is happening with the cloud cover we get during monsoon season?
Yeah, it's a good question, Trevor. And it's actually, maybe this will help. This slide I skipped over because I thought that I kind of already nailed it. So when you look at water balances, again, this is on average over time. So we can have monsoon seasons where the cloud cover is unusually persistent and the temps are low and it's raining all the time. So we actually had this in 2021 and 2022, where you'd end up having these runs of days where there was lots of rain, lots of clouds. And what you saw in those days were sometimes small streams would run for days. And that's because the clouds and the persistent rain had kept the ET down. But as soon as it clears out in Arizona in the summertime, since the sun is so high, and if all the vegetation has already grown, it is going to go bonkers, and it will start pulling water. And again, it's much more effective than free water evaporation because it's got all these little roots everywhere, right? And stuff's growing fast, so it's pumping water out. So you can dry stuff out very quickly. So this is a cool. It's a terrible graphic. It's an old one, but it's a study. They did a water balance study down at Walnut Gulch, down in your neck of the woods, where they have enough instrumentation. Most rain gauges per square unit of area anywhere in the world, maybe, definitely in the country. All this instrumentation. So when it rains somewhere, they know exactly how much, and then they've measured all the water everywhere, and they've measured the soil moisture. So down and again, this is more summer dominated in your region. So we really are talking more about summertime. So 12 inches comes in, and this 10 inches is in surface detention and infiltration. So that's hanging out in the top layers of the soil. Occasionally you get runoff. When the soil is wet and can't hold anymore, it'll run around. Then it turns into channel losses, which is just more detention. And then this is the groundwater recharge. So groundwater recharge is not a big thing in Arizona with our climate. It's pretty rare. It can happen with snow on mountains, and where it can work its way into the mountain block called mountain front recharge. But it doesn't happen in valleys very much because the groundwater is, hundreds, if not thousands of feet away from that water. So when it rains, it's just hanging out for a little while and it's going to be gone. So 12 inches in turns into, on average, 10 inches out. So this is an old study. It's pretty much been backed up in subsequent studies, is that the gain in water that we hold on to is not much in the natural system. But if you're rainwater harvesting or doing other kinds of like permaculture stuff, you got a better chance, right? Because you are actually holding on that water, keeping it from evaporating, putting it where you need it to go.
Just to do a plug, since Mike mentioned it, our WaterWise program, we do consultations for rainwater harvesting. So I think I also wanted to mention something Mike said earlier about our change. And I know I saw Jan Groth on here earlier, who is our master gardener in Cochise County. And she had actually told me that our frost date has changed by about a week in the time that
Yep.
she's been here, that it's just been earlier and earlier. So, but I see we have another question, so I'll hand it back to you.
Okay, thank you. It's actually Christy Brown sitting here with Michael, but Michael, I see temperature come into your equations a lot. Do you study the wind? Because you talked about the hand dryer and the drying effect of wind. How does the wind play in your figures, or does it?
It's such a good question. It's not well represented in these simple, so like these simple estimates don't include wind, but you are spot on. So the gold standard for estimating evapotranspiration is an equation that has wind speed, relative humidity, solar radiation, and temperature in it. And it's the best estimate that we have. Like when we have all those variables together, we can be like, oh yeah, the PET is going to be this. The problem is that we don't have good wind data. Oftentimes it's sparse, it's not measured correctly. It's hard to get into our equations, but we're getting better at pulling data from different sites. And so there are new data sets where we can actually start to use wind. And so read a couple of papers. I'm going to try to fold this into future presentations, but really cool study out of a group kind of broadly Southwest California, New Mexico, where they started to look at and study changes in potential evapotranspiration, but looking at all the different variables. And they did find that wind, changes in wind, either getting slower or faster in certain regions, was enhancing or suppressing that PET even as temperature was going up. So you're spot on. We're trying to do a better job with it.
Thank you.
I got a question in chat that is sort of similar, but maybe slightly different from Cato Daly. So she says, this question may be out of this research, but I wonder if with these more extreme temperature and aridity, what does that mean for wind intensity in Southeast Arizona? So is that intensity of wind going to change, is how I understand it.
Hi, Cato. It is such a good question. We're not sure because so climate projections kind of have this hierarchy of things they do well, and as you go down the list, they get more and more uncertain. Wind is actually, unfortunately, kind of down with precip. And this is actually, it's an interesting question because we've been trying to use wind projections to try to understand where to site renewable energy, like with wind farms, and to not put them in regions where wind will slow down. So the studies have been kind of mixed, and locally they're really unclear if we're going to get windy or not. Some studies actually suggest that we will be less windy because the whole springtime kind of wind gradient will shift north and we'll just get into summer sooner. So we'll have less wind. Some studies suggest it gets parked over us and we get more wind during the spring. And then in the winter and summer, it's kind of a crapshoot. We're not totally sure. Well, really good talking with you all tonight. Really fun, great questions. And, thanks for hanging in there.